All right, 313, let's get going. So the point of these questions is to show you that although for each of these problems you could use a U substitution, eventually you're going to not want to. You're going to want to be like, that's easy enough to do without writing much down, if anything at all, other than the answer. So for this first one, the only real plausible choice is letting U equal the inside of the cosine function, 6x. Your du is going to be 6 times dx. And if you're like me, I prefer to say 1 over 6 times du is equal to dx. So that when I rewrite my integral or translate it to the language of my other variable u, I can't stress enough. Even though I really want to write cosine of u first, I'm going to make sure that I turn dx into whatever it's equal to in terms of du. Right? That doesn't just become du, it's 1/6 times du. So the dx is 1/6 times du, and the cosine of 6x is cosine of u. And then we can anti-differentiate. If you prefer, you can pull out the 1/6. I don't think you need to, but often people just skip to that step and say, oh yeah, the 1/6 multiple is out in front. Now we're going to anti-differentiate. The antiderivative of cosine of u is sine of u. Slap on a plus c. Finally, replace the u with the thing it was equal to. So we get 1/6 times sine of 6x plus c. If you got questions, you should go ahead and ask them. Otherwise, I'm going to keep going on to the next one. Similar idea here. The stuff that my u is going to be is the stuff that's stuck in the denominator. U, if you want to rewrite this, you could write this as 4x plus 3 raised to the negative first power, just to make it a little more obvious or blatant that, oh yeah, the 4x plus 3 is really kind of stuck inside some other function or inside some parentheses. That makes it an excellent candidate for you. It might not be the right choice, but we're going to try it anyway. It is the right choice, but so our du is 4 times dx, or 1/4 times du is equal to dx. So rewriting my integral, again, I'm making sure I take care of dx first. Dx is equal to 1/4 du. I'm going to put the 1/4 out in front and the du right there. So I've dealt with dx, and the rest of this is just 1 over u. Make sure your 4's and u's look different. I struggle with that. So I get 1 over 4, and the antiderivative of the natural log, of 1 over u is the natural log of the absolute value of u. And then we replace u with 4x plus 3, and we get 1/4 times the natural log of the absolute value of 4x plus 3. Okay, so here's the point. And I've said this before, but I'll say it again. When your u substitution would have been a linear function of x, so some like 6x or 4x plus 3 or 2x plus 5 or negative x plus 7 or any line, essentially. If that would have been your u substitution, you can kind of just do the anti-differentiation like you normally would and then divide by the coefficient of x. So I know I'm going to skip that step here, but I'll plug it in a minute. I know that the integral of e to the stuff is just e to the stuff, right? The integral of e to the x is e to the x. So the integral of e to the 9x should be e to the 9x, but then we need to divide by 9 or multiply by 1/9 because the derivative would make us multiply by 9, canceling out the 1/9. So I know the answer, you know the answer is going to be 1/9 times e to the 9x. We're still going to show the work here, but I'm going to encourage you to try to get comfortable with just saying, yeah, I know this is going to be e to the 9x times 1/9, because I can see the derivative is going to be e to the 9x times 9 times 1/9, which is just e to the 9x. But the work we didn't show here was saying, oh yeah, it's a u sub, u is 9x, du is 9 times dx, 1/9 times du is equal to dx. And my integral becomes the integral of my dx is 1/9 du. So there's my 1/9 du. My e to the 9x is e to the u. And you get 1/9 e to the u plus c, which is, of course, 1/9 e to the 9x plus c. A word of caution. This idea that I'm showing you only works if it's a linear function of x. If you were trying to do, say, like, well, I'll point out one that's impossible. It's definitely, if you were trying to integrate e to the x squared, which there is no nice antiderivative there, it's not going to be e to the x squared divided by 2x. Because when you're dividing by something that isn't a constant, you're then introducing the need for the quotient rule if you're going to take the derivative. Here, we don't need a quotient rule, right? Dividing by 9 or multiplying by 1/9 just means that constant hangs out. Here, if you're taking the derivative, you would totally need the quotient rule, and you definitely wouldn't get back to e to the x squared if you differentiated that. So this idea of what we usually call a mini u substitution is where you can just divide by the coefficient of x and things work out nicely. Something else I wanted to say. Oh, I know. Yeah, okay. So a couple more u sub problems, and then I think we will move forward with some new material. But there's a couple problems I just want to show you because I think they're a little tricky and people kind of throw them at you without telling. So I would say some integrals you kind of just have to have done to know how to do them, if that makes sense. Of course, it doesn't make 100% sense because someone figured out how to do it once upon a time without anyone ever showing them, but we're not them. So here's the first one, which is not going to be that. This first one should be relatively easy. An integral of e to the 3x over 2 plus e to the 3x. I want all of you to try to do a u substitution here. And there should be what I would say is a relatively obvious candidate for you that is stuck somewhere. It's not just 3x. It's like stuff in the denominator. Sure. So I would say the things that are stuck are anything that's inside another function. So being in the denominator is inside another function because you're being raised to the -1 power. Or inside a sine, so sine of something, cosine of something, any trig function of something, the something's a good candidate. Or e to the something, or the natural log of something, or the square root of something. Anything that's the argument of a function, the inside part of a function, is a good candidate. It's not always the right candidate, though, right? I should say it's a good guess, right? You're guessing. Is this a good guess for you? Maybe. Let's find out. I think the right choice here is letting u equal 2 plus e to the 3x. Let's find out. I should point out, and I know I've done this a few times, but I often skip the step of saying du dx is equal to the derivative of this, which is e to the 3x times 3, and jump straight to isolating du as whatever that derivative is multiplied by dx. It's fine to skip as long as you remember the reason why we're doing that, right? It's because, oh yeah, we're just saying the derivative of this thing, and then we're just pulling the dx over to the other side. And then I'm noticing that my integral has an e to the 3x times dx. So I would really like one side of this equation to be just that. So I want to see this. Well, I'm going to divide both sides by 3 or multiply both sides by 1/3 to say that 1/3 times du is equal to e to the 3x times dx. Are there other ways to do this? Sure. You could just say dx is equal to du over 3 e to the 3x and then put that in there and then cancel the e to the 3x's that way. That's not the way I like to do it. I would much rather say, oh yeah, this is equal to the integral of, so that part in red, that's my 1/3 du. And then down here, I have just u, which of course I would probably rather write as 1/3 over u times du. The du can go in the numerator or out to the side, right? It's on top, either way you write it. It just shouldn't go in the bottom. And then I suppose if you really want, you could write this as 1/3 times the integral of 1 over u du, although it's completely unnecessary to write that stuff. We should be able to integrate this as is. We know the integral of 1 over u is the natural log of the absolute value of u. So this should be 1/3 natural log of the absolute value of u plus c. And then throw in the u thing, which is 1/3 natural log of, I'm going to write something slightly different, parentheses 2 plus e to the 3x. I would say leave the absolute values, but the reason I'm writing it this way is because oftentimes if you look in the solutions manual of a book, you'll see that they've written parentheses here because in this specific problem, the absolute values are unnecessary because 2 plus e to the 3x is already always non-negative. Right? 2 plus e to the 3x is always positive because e to the something is always positive. So we don't need the absolute values here, but it is totally correct to still write them. You could write it like this and still be 100% correct. It's just that many textbook solutions will not write it that way if they don't need to. Okay, so here's the harder one. Yeah, we need another page. So the reason we did that one is so now we can do this one. The integral of, which way do I want to do this? Which way do I want to do this? Sure, let's go that way. 1 over 2 plus e to the 3x dx. So you might notice that making the same choice for u here is going to be problematic. Because last time I picked u equal to 2 plus e to the 3x, my du was e to the 3x dx essentially, and I had that. I don't have that here. So what do we do? Well, this is where you have to know what to do to know how to do it, which I know sounds stupid because it kind of is. But so I'll show you the pathway that some people take to get there, and then I'll just tell you the trick. Here's the path some people take, which I don't know how you come up with this, to be perfectly honest. We're going to rewrite this in the following way. 1 over 2 plus, we're going to rewrite e to the 3x as 1 over e to the negative 3x. Why? Because who knows what to do. And then we're going to common denominator in the denominator. So we're going to rewrite this as the integral of 1 over, so I need to multiply the 2 here by e to the negative 3x over e to the negative 3x. I know it seems really silly, but we are going to get to where we need to be because of this. Finally, we're going to combine the fractions in the bottom. We probably could have done that in one step. Oh, well. So in the denominator, we have 2e to the negative 3x plus 1 divided by e to the negative 3x. And then, if you have something divided by a fraction, you can multiply by the reciprocal. So 1 divided by all that is really 1 times e to the negative 3x over 2e to the negative 3x plus 1. So then we can rewrite this as e to the negative 3x over 2e to the negative 3x plus 1 dx. And now you might see that if we let u equal this new denominator, the derivative is going to be some multiple of e to the negative 3x, which we have in the numerator. This is the long way of getting there. Let me tell you the short way. The short way of getting to this point is to take your original expression and multiply the top and bottom by e to the negative 3x. Or whatever the opposite sign power of your e to the thing is in the bottom. So if you see something like this and you're like, I don't think there's a good u substitution to do here, a common tactic is to multiply top and bottom by e to the negative of that number or power. Because then, look, it's going to be exactly the same. It's e to the negative 3x over 2 times e to the negative 3x plus e to the 3x times e to the negative 3x is e to the 0, which is 1. So that's the short way of doing that. I'd only ever seen it this way until like last year. Someone was like, well, you can just do this. I'm like, well, that seems insane, but it works. So either way, we've gotten to this place where now we can do a u substitution. So we're going to let u equal the denominator, 2e to the negative 3x plus 1. And our du is going to equal 2 times e to the stuff times the derivative of the stuff times dx. And just for the sake of doing it a slightly different way for once, I'll isolate dx here, even though it's not the way I like to do it. So we'll write du divided by 2 times negative 3 is negative 6 and e to the negative 3x. equal to dx. Again, I don't think this is great, but some people really like doing it this way. So if you do it this way, it's totally fine. I'm not casting aspersions on anyone. I like to do it the other way. But we can rewrite this as being equal to the integral of, so when you do it this way, you are going to get an integral that for a moment has u's and x's in it, which we can never stop at. So we're going to have e to the negative 3x over 2 e to the negative 3x plus 1. And our dx is getting replaced by du divided by negative 6 e to the negative 3x. And immediately, the thing that is beneath the du, I should say the variable thing that is beneath the du needs to get canceled. So that e to the negative 3x there better get canceled with the e to the negative 3x there. And it does, obviously. And now we can rewrite the rest of this as the integral of 1 over u, right? Because that bottom part is our u. And then you have a du over negative 6, or times negative 1/6 out in front. And then the rest of this is the same sort of stuff. Either negative 1/6, the integral of 1 over u is the natural log of the absolute value of u. Throw on a plus c, and then replace the u with what it was equal to, which was 2e to the negative 3x plus 1. Do you need the absolute values? Absolutely not. But I'm still writing them in. It's not wrong to write them. It's always safer to write them. Bless you. Because if you needed them, they would need to be there. And if you didn't, it's still not wrong to write them. It's a kind of a funky problem. But it does come up every once in a while. Let's see. I feel like I had one or two other things I wanted to mention. Oh, yeah, sure. Oh, those are fine. So here's what I would say kind of broadly. When you have an integral and you can't just anti-differentiate it because you don't know what the answer is right off the top, usually thinking about trying a u substitution is a good first thing to try. Is there a plausible candidate for you? Try it out. It might not work. You might have to try something else, but u sub is always my go-to first thing I'm going to try because it's usually the easiest thing we can do, to be really honest. U sub is like the easiest method of integration after just being able to do it straight away. Let's see. But I feel like we might as well start talking about what's coming up next because you guys are going to have 2 classes before I see you again. So let's move along. And don't worry, we're not done with u sub. It's not going away. It's going to be around for the rest of the quarter, probably for the rest of your calculus career, to be honest. Because when you take less so in 21C, but there's still some integration. There's definitely some integration in 21C. Not a lot, but there's some. But in 21D, there's lots and lots of integration, and u sub comes up all the time. So these things you're learning in this class are going to be persistent through the rest of your mathematics career, at least in calculus. But probably if you take other math classes as well, like in 22A and 22B, probably not so much in 22A. There's not much integration, but in 22B, I think there is some. So you want to retain these things is what I guess I'm trying to say. That said, let's talk about another method. I was going to say something else though. Oh, yeah, we'll get there. So let's talk about integration by parts. Often abbreviated as IBP. And from the get-go, here's what I would say. Integration by parts is a method of rewriting your integral so that it becomes an easier integral. So this is going to be a method where we're going to rewrite the original integral to get an easier integral. So I would point out that u substitution in a lot of ways is undoing the chain. You're trying to kind of figure out what the inside was and what the derivative was and trying to make that thing undo. And you typically get like some f of g of x as your answer, right? Like I don't love these previous examples for that particularly. But no, yeah, kind of like in this example here, right? We were finding the inside here and our answer is this, and the derivative, you use the chain rule and get 1 over that stuff times the derivative of that stuff. And you're kind of looking for the derivative to show up. That's why we need the derivative of the stuff to show up so that the chain rule kind of works and gets undone. In a similar-ish way, integration by parts is kind of like undoing the product rule of differentiation. So let's start with the product rule to see what it means. So we're going to say that, yeah, the derivative of f times g is f prime times g plus f times g prime. For some really smart reason, people decided that they wanted to use the letters u and v instead of f and g for this, which is terrible because if you're like me at all, you're using your v's might look pretty similar to each other. So definitely when you're writing this, try to make them look not so similar. So we're going to have u times v. The derivative of u times v is equal to, so we're going to call u prime du. And we're going to call v just v. And then u, and then our g, our v prime, we're going to call dv. And now we're going to anti-differentiate both sides. We're going to say that the antiderivative of the derivative of u times v is equal to the antiderivative. I'm going to switch the order here of v times du plus the antiderivative of u times dv. Let me ask you a question that I hope you all know the answer to. What's the antiderivative of the derivative of u times v? Just the thing we had there, just u times v. So we really have u times v is equal to the antiderivative of v times du plus the antiderivative of u times dv. And then we're going to isolate the integral of u times dv. So we're going to rewrite this as the integral of u times dv all by itself equal to u times v minus the integral of v times du. And the idea here is that we're going to start with this, the integral of u times dv. We're going to identify the thing that is u and the thing that is dv, and then we're going to rewrite this integral as u times v minus the integral of v times du. And the point of this is that this new integral, this should be easier to calculate than the integral of u times dv. That's the point. I would also mention that typically when you're trying u substitution, you're trying a u sub when you think you see something that has a nice derivative somewhere else. But we're also trying u sub a lot of time when we have what we usually refer to as a mixture type of integral, meaning you have two different types of functions, either logarithmic or x to a power or trigonometric or e to the x, or maybe even an inverse trig. Those are kind of like the 5 different categories of functions we usually see in integrals. And if you have two types multiplied together, that's usually what we would call a mixture, and we would try either u sub or integration by parts. So this is the integration by parts formula. I would point out you want to memorize it, and someone I know came up with a very memorable acronym. Acronym's not the right word. Saying, I don't know. So the integral of u dv is equal to ultraviolet, right? UV rays, ultraviolet, super, that's what the symbol there, voodoo. Ultraviolet super voodoo. It's definitely a thing people say, believe it or not. So that's one way to remember what the integral of u dv is. It's ultraviolet minus super voodoo. But we don't say the minus part. Just know it's minus. Okay, so we're going to do some integrals that are mixtures. And some of them are going to be u subs, and some of them are going to be integration by parts problems. But before we do that, let's actually just do an integration by parts problem so you can see what's going on here. So let's say that we wanted to find, say, sure, I like this one, the integral of 2x times cosine of x dx. I cannot say strongly enough, this integral is not equal to x squared times sine of x. We cannot integrate each factor separately and multiply the results together. Why not? Because if you took the derivative of this, you would have to use the product rule. And the derivative of this using the product rule is not going to be that. The derivative of this using the product rule, which is the rule you have to use for the derivative of a product, would be 2x times sine of x plus x squared times cosine of x, which is not equal to 2x times cosine of x. So we have a mixture. Bless you. We have a power of x times a trig function. And for mixtures, we either try u sub, usually we try u sub first, but we're going to skip it here because there isn't a good choice for u sub, or we try enrichment parts. I will also point out, just to backstep a little bit, if you are trying a u sub, there's one thing you never want to choose for u. You never want to choose u equal to x in the u sub. Because if you did the u sub with u equal to x, you're literally just changing all the x's into u's, and you still have the exact same integral, just with the letter u instead of the letter x. You haven't made any progress. On the other hand, for integration by parts, it's totally fine and normal, and often we do pick u equal to x. So just a word of warning. So for this integral here, I'll tell you how to pick u in a minute, but I'm going to start by picking u equal to 2x, and then dv is the rest. Which in this case is cosine of x times dx. I'll point out u times dv must equal the entire thing. So once you've chosen u, everything else that's multiplied by u is what you're picking for dv. And then we're going to find the other two pieces we need. We need the derivative of u. We need du, which is 2 times dx. And we need the antiderivative of dv. The antiderivative of dv is v, and it's equal to the antiderivative of cosine of x, which is sine of x. So now we're going to say that the integral of 2x times cosine of x is equal to, dx, don't forget the dx. I'm not actually going to write uv minus the integral of v du. I'm going to write what u and v are equal to. I'll underline them. So I'm going to have u times v, so 2x times sine of x. That's my u times v minus the integral of v, which is sine of x, times du, which is 2 dx. And look, our new integral that's there is much easier to compute. We know what the antiderivative of 2 times sine of x is. It's 2 times negative cosine of x. So finishing this problem, we get 2x multiplied by sine of x minus negative cosine of x times 2 plus c. Or written in a more typical fashion, 2x times sine of x plus 2 times cosine of x plus c. And that is the antiderivative of 2x times cosine of x. How do I know? Because if we take the derivative of that, we'll get back to the function we should start with. And we will with this one time. The derivative of 2x times sine of x plus 2 times cosine of x. I don't need to write the plus c because its derivative is 0. Is going to be, well, let's see, I'm going to use the product rule. It's going to be 2 times sine of x plus 2x times the derivative of sine is cosine plus the derivative of 2 cosine x is 2 times negative sine of x. And look, the 2 sine and the 2 times negative sine add up to 0. So we're left with 2x times cosine x exactly as we should be. So it works. Okay. So a couple things about how to proceed for integration by parts. So how do we pick things? Well, the general rule of thumb is the following. You want to pick u in a way so that the derivative of u is simpler than it was, simpler than u. So some examples of better choices for u. A great choice for u is the natural log of x, because the derivative is just 1 over x, and 1 over x, or x to the negative 1, is less complicated than the natural log of x. And yeah, it's very vague what we mean by complicated here, but I hope you all can kind of feel the same way. Yeah, the natural log function is much more difficult to deal with than the 1 over x function in a lot of ways. In a similar way, x to a power is usually considered to be simpler when you differentiate it because the power becomes 1 less. So those are usually good choices for you. So things like the natural log of x or x to a power. On the other hand, and then, so really the truth is, and then whatever's left over is your dv. But I will also point out that we pick dv in a way, or really, we make sure that the leftovers satisfy, right? Pick the leftovers after picking u. We want these things to not get more complicated when we anti-differentiate them. So that they don't get more complicated when we anti-differentiate. Some examples are e to the x, right? E to the x, when you anti-differentiate it, stays the same. It doesn't get more complicated. Or a lot of trig functions. Cosine of x and sine of x are both excellent candidates to not get more complicated because when we anti-differentiate them, they're just another trig function. They're really the same. I mean, they're not the exact same, but sine and cosine are just the same function shifted pi over 2 in some direction. So when you anti-differentiate cosine and you get sine, it didn't get more complicated. When you anti-differentiate sine and you get negative cosine, it didn't get more complicated. When you anti-differentiate secant squared and you get tangent, it got less complicated actually, but it certainly didn't get more complicated. So all this boils down to is we usually pick u in the following order. First, a log. Yeah, if you have a natural log, or hopefully not a log with a different base, but any logarithm is always your first choice for u. So if your integral has natural log of x and you're thinking integration by parts, u should be the natural log of x. And then if there aren't any logarithms, hopefully there won't be any of these either. But the next thing we pick is u to be an inverse trig function, which I know I didn't list over here, but I would pick out that inverse trig functions are complicated, like inverse tangent of x, and their derivatives are less complicated. The derivative inverse tangent of x is 1 over x squared plus 1, which, yeah, is less complicated. Again, complicated being a very, very vague notion here. And then after that, we pick u to be any power of x, or whatever your variable is. People often say algebraic term here. I like to say any power of x because I feel like it's a little more explicit about what kind. So like x to the third, x to the negative fifth, x to the 1/2, the cube root of x. Anything that's x to a power, that's usually your next choice for u. And then kind of your last choice for u is a trig function. And I was actually thinking about this. I don't know why we include the last part of this, but the last thing you could potentially choose for u is an exponential function, like e to the x. But you almost never pick u equal to e to the x because there's always something else first. There's like one super random, terrible example of a thing where you pick an e to the something along with some other terrible bits to be your u and your integration by parts, but like it almost never happens. So almost never. The one exception is if you have something like e to the x times sine of x, technically you could pick u and dv to be either thing and it'll work out fine, but we usually just follow the method of madness here. All right. Let's do some examples. So the following examples, we are going to, well, yeah, we're gonna split the difference here. So let's look at these two examples. Let's say on the left side here, we have the integral of x times e to the x squared. And on the right side here, we have the integral of, I like x times e to the 2x. They look very similar, but they are very different. One of these is going to work much better if we do a u sub. And by much better, I mean at all. We can't use either method here. Like for one of these, one thing will work and the other thing won't. And for the other one, the vice versa. One of them is going to work, one's not. So for this first one here, I'm definitely thinking u substitution because I see a choice for u, x squared, that's stuck inside the exponent and whose derivative 2x is essentially in the integral. I'm just off by a multiple of 2, which we can totally fix. So our 1/2 times du is equal to x times dx. And so then we continue on. We rewrite this as the integral of, let's see, x dx is my 1/2 du. E to the x squared becomes e to the u. We anti-differentiate. We get 1/2 times e to the u plus c, and then replace u with x squared, and we get 1/2 e to the x squared plus c. And if you took the derivative of that, you would totally get 1/2 e to the x squared times 2x, which would be x e to the x squared. So this one was a u sub. And even if it wasn't a u sub, I would still think about doing a u sub first because it's easier. At least to me, it feels easier. So here, even though I'm pretty sure it's not going to be a u sub, I'm still going to think, what if I tried a u sub? Let me ask you all, what's a plausible candidate for you here? Yeah, I hear you all whispering it. Yes, I would try u equal to 2x. But then my du is going to be 2 times dx. My 1/2 du is going to be dx. And when I start rewriting this, I have a leftover x here. My dx is 1/2 du. My e to the 2x is e to the u. And my x, if I do a back sub, 1/2 times u is equal to x. So I get a u here and a 1/2 here. I really haven't changed the problem all that much. I still have a variable times e to my variable. So it's kind of the same. I didn't really make any progress here. This is not the way to go. At this point, you could now do integration by parts if you wanted to, but we might as well just start with integration by parts from the get-go. So not a u sub. So instead, we're going to try integration by parts. And I want to point out, both of these are what I would classify as a mixture type of integral. It's a power of x, x to the first, times an exponential, and e to the something. Mixtures. All right, so using my acronym, LI8, do I have a logarithm? Absolutely not. Do I have an inverse trig? Definitely not. Do I have x to a power? I sure do. X to the first. So my u is going to equal x to the first. Again, u equal to x is a no-go if it's u substitution. U equals x is fine if it's integration by parts. And then everyone should write down what dv is. It'll take you less than 10 seconds. So dv is the rest. It's e to the 2x times dx. Each d thing, your dv and your du, there should always be a dx on the other side to match with it. So when I find du here, it's going to equal 1 times dx. And when I find v, I'm just going to have the antiderivative of v. Oh, so here's the reason we spent the time doing the mini u substitutions. I don't want you to get to this place in integration by parts and be like, oh, the integral of e to the 2x, I have to do a u sub for that. You don't have to do a u sub for that. You know it's going to be e to the 2x divided by 2, or e to the 2x times 1/2. That is the reason really for spending time doing those mini u subs, is so that when you get to this part in integration by parts, you're not then using another process to find that antiderivative. All right. So now we're going to say that the integral of x e to the 2x dx is equal to u times v, so x times 1/2 e to the 2x, minus the integral of v times du, 1/2 e to the 2x times dx. You do not have to label these things, but it's good the first few times just to make sure that you got the right stuff. Oh, yeah. And then, just like last time, our new integral, so just like last time we were doing integration by parts, our new integral is much easier to compute. This first part here, I'm going to rewrite it slightly as 1/2 x times e to the 2x minus 1/2 times the integral of e to the 2x, again, is e to the 2x divided by 2, or times 1/2. And yes, you could rewrite that to simplify it even further, but you also could not. That's our answer. Few more examples, sir. Sure, yeah. So some more comparing and contrasting. Let's look at, say, sure, on the left-hand side here, what have I got? The integral of x cubed times natural log of x dx versus the integral of 1 over x natural log of x dx. Okay. One of these is a u sub, and one of these is integration by parts, we think. So let's think about which one might be a u sub first of all. So let's see, is this one a u sub? Well, what are my potential choices for u? I could see either picking x cubed or natural log of x. If I pick x cubed, my derivative is 3x squared, no dice. If I pick natural log of x, my derivative is 1 over x, also no dice. So probably not a u sub. We look over here, if I pick u equal to the natural log of x, the derivative is 1 over x, and we have a 1 over x. It might help to rewrite this as the integral of 1 over natural log of x times 1 over x dx. And then be like, oh yeah, my u could be the natural log of x, and the derivative of that is 1 over x, and then multiply by dx. So we exactly have our du right there, and the natural log part here is our u. So we can rewrite this as the integral of 1 over u times du. Then we anti-differentiate. We get the natural log of the absolute value of u plus c. And then we plug back in u equal to natural log of x, and we get the natural log of the absolute value of the natural log of x plus c. And we do need the absolute value there, because natural log function is not always positive. It's sometimes negative, really close to 0. So you might have noticed when I'm thinking u sub, when I'm looking for u sub, I'm really looking for picking something that is u, so its derivative is also in my integral. That's why I knew natural log of x was going to be a good choice here, because its derivative, which is 1 over x, is also sitting right there. Over here, not the way to go. This is so this one's a u sub, in case it wasn't clear. This one's going to be integration by parts. Again, we already talked about the potential choices for u and a u sub, and they weren't going to work. So, using our acronym, what should our choice for u be here? The natural log of x, the natural log of x. It's challenging because people really often like, oh, u should be x to the third, right? Like it seems like the easier choice. That's true unless there's a natural log as well. So here we're going to pick u equal to the natural log of x, and the rest is dv. So dv is everything else, x cubed multiplied by dx. Integration by parts only works if everything is already multiplied together. You can't really have stuff added together in an integral, then you should break it up in the first place. So then we're going to rewrite our integral, x cubed times natural log of x dx is equal to u. Oh, I didn't find the other stuff. Sorry, I got ahead of myself there. My du is 1 over x dx. My v is the antiderivative of x cubed, which is x to the fourth over 4. So now my integral should equal u times v. So natural log of x times x to the fourth over 4 minus the integral of v times du, x to the fourth over 4 times 1 over x. The whole point of this process is that our new integral is simpler. But sometimes that means you have to simplify it before you can do anything with it. So we're going to rewrite this as the natural log of x times x to the fourth over 4 minus 1/4 times the integral of x to the fourth divided by x is x cubed. And now we can antidifferentiate that with ease. We're going to get the natural log of x times x to the fourth over 4 minus 1/4 times the antiderivative of x to the third is also x to the fourth over 4. And then if you really wanted to make your answer look slightly nicer, you can write it as x to the fourth times natural log of x all divided by 4 minus x to the fourth divided by 16. Let's see. That's probably not super necessary. All right. Just trying to think about something here. The meeting I'm supposed to go to at 4 o'clock. I don't really want to go to it though. So I assume you'll have the will to stay for another 20, 30 minutes? 30 minutes, not 20 minutes, 30 minutes. Yes. I mean, I should point out, you can leave whenever you want, right? I mean, technically, some of you are supposed to be here for attendance purposes and you want to pass the class, whatever, but you're here because you're choosing to be here. I'm not trying to point, like, I didn't feel like anyone was trying to leave. I was trying to point, like, I was trying to be like, maybe I could go, but no, we should stick around because there's so much more to say. Really emphatic there. I just wanted to point out there's a lot more to say. Okay. So let's do one more of these kind of comparison things, and then we'll talk more about how terrible integration by parts can really be. Because it can be really extra terrible. Sure. So I'm gonna give you all this one. All right. So before I even write down another one, the integral of x squared times cosine of 5x cubed. Are we thinking integration by parts or thinking u substitution? It's obviously a u sub, in my opinion, right? We were trying to make it obvious that, oh yeah, the stuff inside the cosine function, if you take its derivative, you're essentially getting the x squared up there. Yeah, there's some constant, we don't care. Versus something much more evil, x squared times cosine of x. It doesn't look that much worse. It is much worse. Such is life. So let's do the easy one first. U is 5x cubed. Our du is 15x squared dx. 1/15 times du is equal to x squared times dx. So here is our x squared dx. That's going to be replaced with 1/15 du. So we're going to get 1/15 times the integral of du. And then the remaining cosine of 5x cubed is just going to be cosine of u. We antidifferentiate. We get 1/15 times positive sine of u. Let's see. Finally, we plug back in and we get 1/15 times sine of 5x cubed. Let's see. U substitution is usually pretty nice. It's usually not terrible. Yes, there are some exceptions, especially when you have like a U sub with a back sub, it can be more terrible. But for the most part, U substitution is relatively great. On the other hand, integration by parts can get ugly fast. So I think there's an obvious choice for our U and our dv here. According to our acronym, Lie8, we should pick U equal to which thing? Yeah. U is going to be x squared, any power of x. And then our dv is the rest. So then we're going to find the rest of the things. Our du is 2x times dx. Our v is the antiderivative of cosine, which is sine. And now we're going to rewrite the integral. Our integral is going to be equal to u times v, which is x squared times sine of x, minus the integral of v times du, sine of x times 2x dx. It is totally fine if you first want to write uv minus the integral of v du. Then you actually have to plug the things in terms of your original variable x. Here's the bad news. This integral, while easier, is not easy enough that I know how to anti-differentiate it without using integration by parts again. There's two different schools of thought here. I tend to prefer to factor out any constants, but if they're not too terrible, like a 2, you might just leave them in. So let's do integration by parts again. And now for this new integral here, for integration by parts, our u is going to be 2x. Our dv is going to be sine of x. Our du is 2dx. Our v is the antiderivative of sine, which is negative cosine. So here's what we're going to get. This is now going to be equal to, now there's still this x squared sine x out in front, minus the entire integral. And that entire integral is equal to this blue u times this blue v minus this blue v times the integral of this blue v times the integral of du. Sorry, integral of v du. Apologies. So it's going to be 2x times negative cosine of x minus the integral of v times du, negative cosine of x times 2 dx. So just to make sure we're labeling things correctly here, this, I'll just point out, this is my u and v in my first situation. That's my v and my du. This is still my original u times v from the first integration by parts. And this is my new u times v minus the integral of v times du. Also, that's why we don't label them, because then you're like, which u is which? That's why you just leave it alone. But you can reuse u and dv the whole time. Whereas if you have to do a problem where you have like multiple u substitutions, you kind of have to use new letters every time you do it. All right, so I'm going to do two things at once. Really? Yeah. I got x squared times sine of x minus 2x times minus cosine is plus 2x cosine x, and minus a minus a minus, right? Because this minus and this minus come out to be minus the integral of 2 times cosine of x, which we probably could have also just written there, but fine, we didn't. Finally, we get x squared times sine of x plus 2x times cosine of x. The integral of cosine is sine, so we get minus 2 sine of x plus c, and that's our answer. So sometimes you have to do integration by parts multiple times. There are 3 particular examples I can think of where you would have to do it lots of times. Let me say what I mean. So repeated integration by parts comes up most frequently in the following 3 situations. The integral of x to a power times e to the x, or the integral of x to a power times cosine of x, or the integral of x to a power times sine of x. And the reason these are the ones that come up specifically, well, I should point out where the power p is a positive integer. This does not work if your power is some fraction or negative number. But essentially, every time you do integration by parts on one of these things, the power is going to reduce by 1 because you're differentiating x to the power. And the other function, the e to the x or the cosine of the sine, when you anti-differentiate it, either still going to be e to the x or cosine will go to sine and sine will go to negative cosine. So you're essentially just kind of cycling through the antiderivatives while the power gets 1 less every time. The bad news is if your power is 4, you have to do integration by parts 4 times. The good news is there's a shortcut. So here's the shortcut. The shortcut is called tabular integration. Apparently, this also works for other things too, in kind of a weirder way that I'm not super familiar with, and it feels like it's really easy to make a mistake on, so I'm not going to talk about it. But yeah, I remember someone showing it to me last quarter. I was like, oh, that's kind of slick. So let's do the same problem again, but we're going to do it using a shortcut. So we were doing the integral of x squared times cosine of x, I believe. You double check. Yes, we were. Okay, so here's what you do. You still pick u and dv the same way. So our u was x squared, but we're going to make it into like a little table. And our dv was cosine of x. On the u side, we take derivatives, just like we usually do with u. So 2x, 2, 0, all the way down to 0. And then on the dv side, we take the antiderivative. So the antiderivative cosine is positive sine. The antiderivative sine is negative cosine. And the antiderivative negative cosine is negative sine. And then we connect things in the following way. It's going to be x squared times sine. I should say it's going to be positive x squared times sine of x minus 2x times negative cosine of x plus 2 times negative sine of x. The sign always switches. Plus, minus, plus. But then you also have to account for the other signs over here. So this is going to end up equaling, oops, I don't want red. Yes. And then equaling x squared times sine of x minus 2x times negative cosine of x plus 2 times negative sine of x. Let's see. Or written more nicely, x squared times sine of x plus 2x times cosine of x minus 2 times sine of x. Let's see. Which I believe is exactly the same thing we got the other way. Let's double check. Yep, it sure is the same thing. Great, it works. So this thing works in these 3 cases, because these are the cases where your choice for u will eventually, if you take enough derivatives, become 0. Because if you have x to a positive power, I should say a positive integer power, every time you take a derivative, it just gets 1 less, and eventually you get to 0. On the other side, your dv has to be something whose antiderivatives just cycle through the same 1 thing or 4 things, however often. It can get a little bit more complicated if you have, so I should point out, really, this could be more complicated because technically you don't have to have just extra power here. You could have like any polynomial. So you could have like 4x cubed plus 3x plus 1 for your x to a power. And you could have e to the 7x or sine of 1/3 x, right? You could have any multiple of x and still have the same process work out the same way. It's just going to look a bit uglier. So for example, I'm going to make up one that's really super ugly here because sure, why not? Someone could give you something terrible like the integral of x cubed plus 4x plus 2 times e to the 2x. And instead of doing integration by parts 3 times, you could use tabular integration. Okay, great. My u is going to be the terrible polynomial there. X cubed plus 4x plus 2. My dv is e to the 2x. My derivatives are 3x squared plus 4, then 6x, then 6, then 0. I need as many rows for my dv. My antiderivative of e to the 2x is e to the 2x divided by 2. The antiderivative of that is e to the 2x divided by 2 times 2. The antiderivative of that is e to the 2x divided by 2 times 2 times 2. And the antiderivative of that is e to the 2x divided by 2 to the 4th. And then the usual plus that product minus that product plus that product minus that product. So it's going to be gross to write out, but our answer here should end up equaling x cubed plus 4x plus 2 times e to the 2x over 2 plus 3x squared plus 4 times e to the 2x over 4 plus 6x times e to the 2x over 8 plus, oh, I missed some signs there. Good job, James. That should be a minus. Ugh, terrible. It's a minus sign. Minus 3x squared plus 4 times e to the 2x over 4 plus 6x times e to the 2x over 8 minus 6 e to the 2x over 16 plus c. This shortcut is valid. It's useful. I would recommend using it when appropriate. Okay, but that's not the only thing that comes up. So there's lots of interesting things, interesting intervals that can only be approached using integration by parts. For example, the integral of natural log of x. What's our choice for u here? Well, there's only one choice. U is the natural log of x, and dv is the rest, dx, or if you prefer, 1 times dx. All right, our du is the derivative of natural log of x, which is 1 over x. Our v is the antiderivative of 1, which is just x. And then we throw the formula at it, and the integral of natural log of x dx is equal to u times v, x times natural log of x, minus the integral of v times, oops, I forgot my dx here, v times du, which is x times 1 over x dx. Simplify this. You get x times natural log of x minus the integral of 1. And then anti-differentiate that, and you get x times natural log of x minus x plus c. You should be able to do this on an exam because it often gets asked. You should also probably memorize it. It comes up just often enough that it's worth memorizing, but just barely. Let's see. So yeah, sometimes you just like, you only have one thing to pick for your integration parts. You're like, well, that's my u and my dv is dx, like this next problem. Like the integral of the arctangent of x. New exciting times. So in a very, very similar way to the previous problem, we're going to pick u equal to the arctangent of x, and our dv is going to be the only thing left, which is dx. Our du is going to be the derivative of the arctangent of x, which is 1 over 1 plus x squared dx. And again, our v is going to be x. So if we rewrite this, we have that the integral of arctangent of x is equal to u times v. Instead of writing arctangent of x times x, I'm going to write x times arctangent of x, right? Usually we write the multiplication in whichever order feels better. So x times arctangent of x minus the integral of x times 1 over 1 plus x squared dx. You might put the x on top. You don't need to. So this integral over here looks like we could do a u substitution. We could let u equal 1 plus x squared, and our du is 2x dx, and 1/2 du is equal to x dx. So then if we rewrite this, so I don't love writing a thing with x's minus an integral with u's. Like, it just feels kind of weird to me. So I would feel like I'm doing some side work over and be like, okay, on the side, the integral of x times 1 over 1 plus x squared dx is equal to, well, x times dx is my 1/2 du, and 1 over 1 plus x squared is 1 over u. So that's going to be 1/2 times the natural log of the absolute value of u, which is then 1/2 natural log of the absolute value of 1 plus x squared. I'm not writing a plus c here because it's just my own side work. So then when I go over here, it's going to equal x times the arctangent of x minus that. 1/2 natural log of, I'm going to drop the opposite values because 1 plus x squared is always bigger than or equal to 1 plus c. So sometimes you might have to use integration by parts and u substitution to complete an integral. It happens more often than we would like it to. Let's see, what else do we got here? Sure. This one. Yeah. So, well, it's not that the du went somewhere. It's that the x dx got replaced with 1/2 times du. Right, I'm just so I could, if I wanted to, I could rewrite this integral as the integral of 1 over 1 plus x squared times x times dx. Right? Order of multiplication is totally malleable. And then we can say, oh yeah, the x times dx, that's equal to my 1/2 times du because of my u substitution here. Because du is equal to 2x times dx, so 1/2 times du is equal to x times dx. And then this part right here, that's equal to my 1 over u. So I really do have 1 over u times 1/2 times du. Oh, okay. So the thing is, well, let me ask you a different question. So here's what I would say. When you do an integral, like when you do the integral of e to the 3x times dx, and we get e to the 3x divided by 3 plus c, where does that dx go? Well, the thing is, the integral symbol and the dx go together. They're a pair, they're instructions. These two things here, this integral symbol and this dx, those are instructions telling us to anti-differentiate. And after we've done the thing the instructions told us to do, we no longer write the instructions. Very similar to how if I wrote the derivative of x to the 4th is equal to 4x cubed. But I'm not writing the derivative symbol again because I did the thing the symbol told me to do. I followed the instructions, and now I don't need to write those instructions anymore. In the same way, the integral symbol and the dx that goes with it tells you. In fact, really, I should say, the integral symbol tells you anti-differentiate. The dx differential tells you what variable you are anti-differentiating with respect to. Yeah, that's what's happening there. But yes, when you've done the integral, then you just drop. Let's see here. Yeah, we should do one of those. Okay. We're not hitting all the highlights yet, but we're hitting a lot of the interesting points. We'll do one more problem and then we'll call it a day. So let's say we had the integral of, which one do I want to give you? Sure, we'll make it, let's make it a little challenging. Let's make it e to the 2x times sine of x. All right. I'm out of water. Better about this. So, integration by parts. You can actually technically make either choice here. You can pick u to be the trig thing or the exponential thing because it's going to work out the same way. But I'll make the standard choice of picking trig before exponential. So we're going to pick u to be the trigonometric thing. And our dv is the rest, e to the 2x times dx. My du is cosine of x, dx. My v is the antiderivative of e to the 2x, which is e to the 2x divided by 2. Again, See how often these mini u subs come up? That's why we don't want to spend time doing them on their own. So we're going to rewrite our integral of e to the 2x times sine of x dx is equal to u times v. So sine of x times e to the 2x over 2 minus the integral of v du, which is e to the 2x over 2 times cosine of x dx, which doesn't feel great because it doesn't really feel like my integral got less complicated. It's still e to the something times either sine or cosine, which I said before were essentially the same function. Well, if we don't know what to do, we just do more stuff. So we're trying to erase my parts again. Now here's the crux here. You have to choose your u and your dv in the same fashion that we chose it before. If we were to choose it the wrong way, if we were to choose, say, u equal to the e thing and dv equal to the cosine thing, you would just end up undoing the work you just did, and you would end up getting that the integral of e to the 2x times sine of x was equal to the integral of e to the 2x times sine of x, which is true and not helpful. So instead, we're going to make the choice of letting u equal cosine of x. My dv is going to equal e to the 2x divided by 2. And then my du is going to be negative sine of x. And my v is going to be e to the 2x divided by 4. So now our integral of e to the 2x times sine of x dx is equal to sine of x times e to the 2x over 2 minus u times v, which is cosine of x times e to the 2x over 4 minus the integral of v du, which is e to the 2x over 4 times negative sine of x dx. And this might feel like the worst news possible. We've essentially got the same integral we started with. We started with the integral of e to the 2x times sine of x, and we have the integral of e to the 2x times sine of x. And yeah, there's a slightly different coefficient, but it's essentially the same. Well, that's actually good news, because here's what's going to happen. Let's simplify a little bit. So my equation here, I'm probably in the other, yeah, let's just use another piece of paper. Fine. So what we have now is that our integral of e to the 2x times sine of x dx is equal to, I'm going to rewrite things just slightly. It's equal to 1/2 times sine of x times e to the 2x minus 1/4 times cosine of x times e to the 2x minus a minus is minus, we have a 1/4 right there, the integral of e to the 2x times sine of x. And now we're going to do something that always has felt super shady to me, but is totally allowed. We're going to add this to both sides. So if you have one integral of e to the 2x sine x plus 1/4 of the integral of e to the 2x sine x, altogether that's going to add up to 5/4 of that integral. So on the left-hand side, we have 5/4 of the integral of e to the 2x times sine of x dx is equal to, on the right-hand side, 1/2 sine of x times e to the 2x minus 1/4 cosine of x times e to the 2x. And finally, we finish the problem by multiplying both sides by 4/5, which totally feels like some weird stuff has happened, but it is really valid and the only way of finishing this problem. So multiplying both sides by 4/5, we get that the integral of e to the 2x times sine of x dx is equal to 4/5 times all of this. 1/2, I'm going to write the e to the 2x first. E to the 2x times sine of x minus 1/4 e to the 2x times cosine of x plus c. And that is our answer. Sometimes people factor out the e to the 2x or distribute the 4/5, but that's it. Kind of weird, but it's valid. So whenever you see an e to the something times either sine or cosine, this is the process. You do integration by parts twice. You end up getting a multiple of the same integral you started with. You add it back over to the other side and multiply both sides by the reciprocal of the coefficient. Pretty standard fare, even though it seems terrible at first. All right, that's enough for today. I'll see you all on Tuesday, where we'll probably continue talking about integration by parts or other fun methods of integration.